Hello class. In our last lesson we were talking about the Fourier series, and we want to talk more about Fourier series. So we said that a Fourier series is used to expand a function which is periodic as an infinite trigonometric series. Now, we consider a function, say f of x, which is periodic. The function needs to be periodic with some period t, Now, in addition to this, the functions need to be sigma-valued. Sigma-valued means that the function has one output corresponding to each input. So there are those functions like f of x is equals to say 2x, f of x is equals to x raised to power 3, and so on. So whenever you feed an input to this, say x is equals to 3, you get the output is 2 times 3, which is 6. So when the function, say, the input here, you have the domain, you feed a function like 3, a value like 3, the function is defined by f of x is equals to 2x, you get the output, which is 2 times 3, which is 6. You get only one output. So such a function is said to be a single valued function. There are those functions which may not be single valued. A good example is the square root function. Say if you have f of x is the square root of x, then you see that if you feed an input, say you have an input here, x is equals to 2, or x is equals to 9, for example, then you look at what are the outputs. You get the function here, f of x is equals to the square root of x. So that means that we take the square root of 9, and we know that the square root of 9 is either minus 3 or plus 3. So in this case, there are two outputs corresponding to a single input. Such a function is not a single-valued function. So a function which is not single-valued cannot be expressed as a Fourier series. So we require that a function be single-valued. We also require that the function be continuous, either continuous or have a finite number of discontinuities. We simply say the function is piecewise continuous. But in particular, we say that functions need to be continuous or have a finite number of finite discontinuities. So such a function, that is one of the conditions that is required. The function also needs to be piecewise smooth. The function needs to be piecewise smooth. And by a smooth function, we mean a function which is differentiable. The word smooth in functions mean that the function is differentiable. Now, the three conditions, that is the function, we said the first one was that the function be single-valued. These three conditions here, we call them the Dirichlet conditions. So we consider a function which is periodic with some period t, and these functions need to be piecewise continuous. It may be continuous, or it may have a finite number of finite discontinuities. It is single valued and piecewise smooth. Now, if the function satisfies the three conditions, then it can be expressed as an infinite trigonometric series, which we call the Fourier series. The Fourier series will take the form f of x is equals to a half a naught plus the sum n is equals to 1 to infinity an cosine of n pi x alpha l plus bn sine of n pi x alpha l, where in this case a naught, an, and bn, we call them the Fourier coefficients. We call these the Fourier coefficients. L here is half the period. So if the function is periodic with period t, if t is the period, for example, capital T is the period, then L will be t divided by 2, is half the period. Now we can consider a simple case where t is 2 pi, and if t is 2 pi, then L will be equals to pi. And if you have the L here, which is equals to pi, then pi can cancel with this other pi, and you will just have nx. Now, we have the coefficients. We defined the coefficients an. The first one is a naught, which is 1 over L, integral from minus L to L, f of x dx. That's the first coefficient, a naught. The interval of integration is done over one period from minus L to L. Sometimes we may start from 0 and then integrate to 2L, or to the period t. Then we have an, which is defined as 1 over L, integral from minus L to L, f of x, cosine of n pi x alpha L dx. And lastly we have bn, which is defined as 1 alpha L, integral from minus L to positive L, f of x, sine of n pi x divided by L dx. These are the three Fourier coefficients. So now you are given a function. You are told to express it as a Fourier series. You are told to represent the function in a Fourier series. You simply need to find the values of the constants a naught, an, and bn. Once you find the values of these constants, you'll come back and substitute in this series. You substitute the value of a naught, the value of an, and the value of bn. So let's take an example. You are given a function. You are told to find the Fourier series representation. Find the Fourier series representation for the function the function is given as f of x is equals to you have x is equal, x. The function is defined by x in the region between minus pi less than x less than 0. The function is defined by 2 minus x in the interval between 0 and pi. And then the last statement here, f of x plus 2 pi. Now, this last statement simply says that if you look at the last statement here, it simply says that the function is periodic with period this value here, t. So the function is periodic with period 2 pi. The period of oscillations here is 2 pi. And within that region, from minus pi to 0, the function is given by x, the first line here, up here. So you see that the first line says that f of x is equals to x for all values, for all x in the interval between minus pi and 0. Then the next line says that the function, this next line says that the function is defined as 2 minus x in the region between 0 and pi. So the next line says that f of x is equals to 2 minus x for all x between, or in the interval between 0 and pi. Then the last statement, of course, says that the one that we write f of x is equals to f of x plus 2 pi. This one simply says that the function is periodic. This one implies that f of x is periodic with the period t is equals to 2 pi. So the function is periodic with period 2 pi. Now we need to find the value of L. We said that L is half the period, t divided by 2. So in this case, the value will be 2 pi divided by 2, which is pi. And so when we are writing the Fourier series, remember the Fourier series f of x is equals to a half a naught plus the sum from 1 to infinity an cosine of n pi x all over L plus bn sine of n pi x all over L. Now see that L is equals to pi here. So in this case, when we write n pi x divided by L, this quantity here will be equals to n pi x divided by pi, and pi cancels out and we are left with nx. So we can replace the quantity n pi x all over L in this particular example with nx because our period is 2 pi, and our function f of x, now we can write it as a half a naught plus the sum from n is 1 to infinity. Then we have an cosine of nx plus bn sine of nx. So we can have it simply as that. So now, when we write a naught here is defined by 1 over L integral from minus L to L f of x dx. Our L is equals to 2 pi. Sorry, L is equals to pi, not 2 pi. L we have seen is equals to pi. So we can substitute and write 1 over pi integral from minus pi to pi f of x dx. And when evaluating this integral, we will now go back to our function. and check that in the interval between minus pi and 0, in the interval between minus pi and 0, the function is equals to x. So we shall be integrating x from minus pi to 0. Then in the interval between 0 and pi, the function is defined as 2 minus x. So in that interval, we shall be working out the integral of 2 minus x. So these are the values that we substitute here. And therefore we write 1 over pi, integral from minus pi to 0. In this interval, the function is defined by x. Then we now go to the next interval from 0 to pi. And in this interval, the function is defined by 2 minus x. So we integrate with respect to x. So notice that we have the integration is carried out over one period. The interval from minus pi to pi, that is from minus pi to 0, then from 0 to pi, that length is equals to 2 pi radians. Now we can work out the integral. We get 1 over pi. The integral of x will be x squared over 2. And this we integrate from minus pi to 0. Then plus 1 over pi. We integrate 2, we get 2x. The integral of x is x squared over 2. The interval of integration is here is from 0 to pi. So we substitute that. So in this case, the first value here, we get 1 over, we can push the 2 outside here so that we write 2 pi. See that this 2 here can move outside here. Then we shall have x squared inside. Then when x is 0, the upper limit, we have 0 squared. And when x is minus pi, we have minus pi squared. Then we have 1 over pi. When we substitute the upper limit, 2, we get 2 pi minus pi squared over 2. Of course, the lower limit will have when we substitute the lower limit x is 0, we get this is the value at the upper limit. When we substitute the value at the lower limit, we definitely get 0. So we can now simplify this. The first value here, we have 1 over 2 pi. Then this will be minus pi squared. We can factor out pi in the second interval here. So we have pi divided by pi. Then we get 2 minus pi over 2. This will give us pi over 2 here is negative. Then the other one will be plus 2 minus pi over 2. And the value of a naught becomes 2 minus pi. When we work out, this is the value of a naught. That's the value of a naught. We can now work out the value of an. An, the definition for an. Definition for an is 1 over L, integral from minus L to L, f of x, cosine of n pi, x divided by L dx. But because our pi, L is equals to pi, we will now substitute and write 1 over pi, integral from minus pi to positive pi. Then we have f of x, cosine of nx dx. Notice that now, because L is pi, L here is equals to pi, so we shall have pi cancelling out and we are left with nx. Then we remember that our function is defined in such a way that in the interval between the 0 and we start from minus pi. In the interval between minus pi and 0, in this interval, the function f of x is equals to x. So we shall write, in this case, an will be 1 over pi, integral from minus pi to 0, x cosine of nx dx. Then, in the interval between 0 and pi, the function f of x is defined as 2 minus x. So we shall substitute the second interval and write 1 over pi, integral from 0 to pi. And in this interval, the function is here, 2 minus x, cosine of nx. We integrate with respect to x. So we now need to carry out these two integrals. And to carry out these integrals, we use the method of that we call tabular integration. With tabular integration, remember, we require that one of the functions be polynomial. Otherwise, we would have applied the method of integration by parts directly. So, but here, because we have the x and cosine of nx, so we have cosine of nx, we need to differentiate x. The derivative of x is 1, and if we differentiate 1, we get 0. Then we need to integrate now the cosine of nx the same number of times we have done the differentiation here. So the derivative of cosine of nx will be 1, not the derivative, we need to integrate. So the integral of cosine of nx is 1 over n sine of nx. And then we integrate again, we get minus 1 over n squared cosine of nx. Then we'll be multiplying x by 1 over n sine of nx, and 1 by minus 1 over n squared cosine of nx. Then there will be the signs as the integration by parts formula. The first one is usually plus, the second one is minus. We do the same to the second quantity here. So on one side we have 2 minus x, then cosine of nx. The derivative of 2 minus x is minus 1. The derivative of minus 1 is 0. Then, of course, the integral of this becomes the same as what we had on the other side. 1 over n sine of nx and minus 1 over n squared cosine of nx. Then we multiply out. We multiply out those terms. Remember, don't forget the signs. So, working out, when substituting back here, don't forget the coefficient here, 1 over pi. The coefficient here, 1 over pi. So we shall write therefore an is equals to 1 over pi. Then we have the terms x alpha n sine of nx plus 1 alpha n squared cosine of nx from minus pi to 0. Then in the second integral we have 1 alpha pi, and we get 2 minus x alpha n sine of nx, then minus 1 alpha n squared cosine of nx. And the interval, the range of integration is from 0 to pi. So we work out this. It is important to note that when we are evaluating sine of nx, when we put the upper limit, we get sine of 0, which is 0. And when we put the lower limit, we get sine of n pi, which is also 0. So clearly, this quantity will be 0. The same with this one. So we only need to worry about the cosine term. So we can reduce, even before inserting the limits, we can reduce our function or our value as 1 alpha n squared pi cosine of nx, n increasing from, or x increasing from minus pi to 0. Then in the second term, we have minus, this will now be minus, not plus, minus 1 alpha n squared pi, and we have cosine of nx from 0 to pi. So we work out this, and in the first term we have 1 over n squared pi, then we have cosine of 0 minus cosine of n pi, and 1 over n squared pi, we have cosine of n pi minus cosine of 0. Now we note that 1 over n squared pi is common in all the terms here. So we have cosine of 0, which is 1. Cosine of n pi is minus 1 raised to power n, as we had seen earlier. Then in the second terms we have minus, and we have minus 1 raised to power n, which is cosine of n pi, then cosine of 0, which is 1. We can work out this. And now notice that here we have 1 minus 1, yeah, which will be 2. So we can write 1 over n squared pi, and then we have 2. Then we have minus 1 raised to power n here, minus. You see the sign here is minus, then we have minus, the same quantity, so we have minus 2. When we add them, we get 2 now. Minus 2 into minus 1 raised to power n. And we can factor out 2. We get 2 over n squared pi. Then we shall have inside the brackets 1 minus 1 raised to power n. Now, when working out this, you see that minus 1 raised to power n can have only 2 possible values. The case when n is even will give us 1 minus 1, which is 0. The case when n is odd, this quantity minus 1 raised to power n becomes minus 1, so that we have 1 minus 1, which is 1 plus 1, giving us a value of 2. Now, since the value of a0 will vanish when n is even, then we only need to consider the cases when n is odd, and then the value here becomes 2. So that we multiply 2 by 2, which is 4. So we need to write only the coefficients. The coefficients only the case where the n is odd, and we use now what we call the n number generator, 2n minus 1, which will now give us 4 divided by 2n minus 1 squared times pi. This is the value of an. And finally, now we need to find the value of bn, and we work out the same way. So we write bn is equals to the integral from minus L to L. We have 1 over L. Then we get f of x sine of n pi x all over L, and this reduces to 1 all over L, 1 over pi in this case, integral from minus pi to pi, f of x sine of nx, when we replace L with pi, because L was pi. Now, we know how the function was defined. So we have 1 over pi, integral from minus pi to 0. In this interval, the function was x. So we have sine of nx dx plus 1 over pi, integral from 0 to pi. In this interval, the function is defined by 2 minus x. So we multiply by sine of nx dx. We work out these integrals using tabular integration. So on the first one, we have x and sine of nx. We differentiate x to get 1, differentiate again to get 0. We integrate the sine, we get 1 over n cosine of nx. We integrate again to get minus 1 all over n squared sine of nx. We do the same here. We have 2 minus x and sine of nx. We differentiate the quantity here, we get minus 1, then 0. Integration will give us minus 1 over n sine of nx and minus 1 all over n squared. Sorry, this is not sine. The integral of cosine, sine is cosine. This one should be cosine of nx. And in the second integral will give us minus 1 over n squared sine of nx. Then we multiply as before, and don't forget the signs here, plus and minus. The same here, plus and minus for this one. So when we substitute these values now back, we get bn is equals to, remember we had the coefficient 1 over pi, then this will be minus x all over n cosine of nx plus 1 all over n squared sine of nx from minus pi to 0. Then we have plus 1 all over pi minus 2 minus x all over n cosine of nx minus 1 all over n squared sine of nx, and x increasing from 0 to pi. from 0 to pi, the upper limit. We substitute the values again. The sign quantity here is obviously 0, the same with this one. So we only need to consider the cosine. Now we can put the case when x is 0. When x is 0, we put x is 0 here, and this quantity becomes 0. So we get Bn will be 1 over pi. Then when x is 0, this becomes 0. Then minus. When x is negative pi, we have minus pi over n, cosine of n pi. Now I'll just write cosine of n pi and not cosine of negative n pi, because cosine is an even function. So cosine of negative n pi is just the same as cosine of n pi. Now we have plus 1 over pi. Now we consider the case where x is pi. So in this one we have minus 2 minus pi over n cosine of n pi. Then the lower limit, when x is 0, if you put 0, this will be 2 minus 0, which is 2. So we shall have minus 2 over n cosine of 0. Cosine of 0 is 1. So note the signs here. We have minus, that will give us a negative value. And then we have 1 over pi, and then we have a pi here, so pi will cancel out, and we are left with minus 1 over n times minus 1 raised to power n. Minus 1 raised to power n. That's the first bracket here. Then in the second one, we have 1 over pi. And then we can push this negative in here, so that we have minus 2 plus pi, or pi minus 2. So I'll just write pi minus 2 over n times minus 1 raised to power n, then plus 2 over n. So simplifying this, we can try to simplify this. First here, these are 2 terms, and we can break them, so that we write minus 1 over n times minus 1 raised to power n plus, now the first term here will be, let me just write both of them, pi over n minus 1 raised to power n, then minus 2 over n times minus 1 raised to power n, then plus 2 over n. Now you see, if you open the brackets here, if you multiply each term here by pi over n, this term now will vanish. This pi will cancel out. This pi will cancel this one. So we shall have minus 1 over n times minus 1 raised to power n, then plus 1 over n times minus 1 raised to power n. Then we shall have the other 2 terms, which we can write plus 1 over pi. I'll start with the positive term. Of course, 2 over n is common in the last 2 terms here. You see, this one has 2 over n, this one has 2 over n. So instead of writing 1 over pi, I can just factor out that. So I write 2 over n pi. Then in brackets, I'll start with the positive term, 1 minus 1 raised to power n. So I have these two terms, and these two terms will add up to 0. Then I have this one. This quantity here will give me a value of 2 when n is odd and 0 when n is even. So in this case, this will be 0 plus 2 over n pi multiplying the quantity 2 when n is odd and 0 when n is even. So with that, now I can multiply. When n is odd, this will be 4 over n pi. And when n is even, this will be 0. So in this case, because we have the non-zero values only when n is odd, then I can ignore the cases when n is even. So I only generate the odd values. So I use 2n minus 1, and then I'll write 4 divided by 2n minus 1 times pi. This is the value of Bn. So now I have the values. I have the full values of the Fourier coefficients. I have the values of the Fourier coefficients. You see we had a naught is 2 minus pi. Then an we had it here, is 4 divided by 2 minus 1 squared pi. And lastly we have Bn, which is 4 divided by 2n minus 1 times pi. And so I now substitute back. F of x is equals to a half a naught plus the sum n is 1 to infinity. I have an cosine of n pi x over L. Our L was pi, so this one was reducing to nx plus Bn sine of nx again. So now I'll substitute the values. A naught is 2 minus pi, so we divide that by 2. Then I have the sum from n. I can of course separate the two terms here, so that I first write the cosine terms. So I have 4 over pi. Then the sum is for n is 1 to infinity cosine of n pi x. So I'll have 1 over 2n minus 1 squared cosine of 2n minus 1 x. Then the next term is plus the Bn here. I will push out the constant 4 over pi. So I write 4 over pi, then the sum from n is 1 to infinity, 1 over 2n minus 1 sine of 2n minus 1 x. So basically this is how you find the Fourier series representation for a given function. So you can go through this once again and ensure that you understand all the steps. It's important that you go through the work again and understand all the steps clearly.